So we just discussed how the procedure of virtual work to find an unknown displacement. It can also be to find an unknown rotation. And we're going to see how it works in practice on a truss. So I have this truss that's subjected to two loads. One of them should probably be P1. That's okay. Yeah. Let's make this P1. Not that it matters, but. And this is my real system, right? It's subjected to these two loads, P1 and P2. And I want to find the vertical deflection at B, which is the vertical deflection due to these loads that are on there. The vertical deflection at B due to loads P1 and P2. So I am going to draw the exact same system with no loads on it. And this is my virtual system. And I'm going to apply a unit load at B in the direction that I think it's going to deflect. So in my real system, I need to determine my real deformations delta. And that means the elongation of the bars, right? These are axial members, so some of them are going to elongate vertically, some of them are going to elongate horizontally. I've got diagonals in there, so they're going to elongate diagonally. So what I need to do is calculate the internal member forces. Calculate internal force in each member, NI. And I can make like a little chart if I were, just assign it, right? Okay, I'm gonna have like, if this is member 1, N1, N2, N3, N4, N5, N6, N7, N8, N9. So I'm going to solve this whole thing once, get all the member forces once due to my real forces. And then, since these are axial members, right? So my deflection is equal to NL over AE, right? Or PL over AE. I can calculate the deflection in each member. Or the real deformation in each member. Delta I is equal to NI, LI, AI, EI. So each member is going to have a different force. Each member might have a different length, likely. Each member might have a different area and might be made out of a different material, so it might have a different elastic modulus. Those two often are constant throughout, but they might change, so they're in there. And now I have my virtual system. Where I need to determine, all I need to do for this one is determine the internal force in each member. Now earlier we called it big N prime. Now we're going to call it little n for my virtual system, little n. So we're switching nomenclature. We've got little n1, n2, n3, n4, n5, 6, 7, 8, 9. Now, it doesn't matter what you number things as long as you know, right? As long as you keep track that this is number 3 and this is number 3, or they'll probably have letters, but yeah. You need to be consistent in that. It'll be easier when they're actually numbered letters in there. Now, once I have those, all I need to do is use my VirtualWork equation. Delta B, my deflection at B is equal to the sum of the n prime times delta. I just renamed some stuff, so n times my baby delta, which is n, right, hold on, ni times delta I, right? And that is equal to ni times, I'm going to take that equation, right? Ni times ni li over ai ei. And sum it from n equals from I equals 1 to your number of members. Right? So to use the system of virtual work, you basically solve for every member force twice. Once under the actual loads and once under a unit load at the point of interest in the direction of interest. Right? I couldn't say that, I guess. So you basically, you solve your truss twice. Once for real and once with a virtual load. So let's do an example. Right? All of that theory, and it kind of boils down to something that's more about bookkeeping, as trusses tend to be, than anything else. So we have a truss, we have a cross-sectional area and elastic modulus that's the same for all your members, so we don't have to worry about that varying. We want to determine the vertical displacement at C if we apply a horizontal 4 kilonewton force, also at C. So what I basically want to do is I have 3 members, right? AB, AC, and BC. I want to fill out this table. This is my internal member force, my this is my virtual, this is my real, and everything else stays the same. So let's go to my real system first. Let's see. I have reaction at B in the Y direction, reaction at A in the Y direction, and I'm probably gonna have one going that way at A. So let's see. So sum of the forces in the x direction is 0, right? RAX is equal to 4 kilonewtons going to the right. Let me put that up here. See, sum of the moments about A is equal to 0. I've got 4 kilonewtons acting at 3 meters counterclockwise. I mean clockwise, so it's negative. Yep. Then RBY acting at 8 meters counterclockwise, so it's positive. So that equals 0. RBY is 12 divided by 8, right? 4 times 3 divided by 8, 1.5. I know if I do the sum of the forces in the x direction, right? RAX, I'm going to replace it with 4 kilonewtons. RAY is going to be acting down, 1.5 kilonewtons. Because it's going to be equal and opposite of RBY. That's the whole structure, right? Let's find the forces. Look at joint A. Let's see. I've got 1.5 kilonewtons. And 4 kilonewtons. I've got my force in member AC, force in member AB. If I take the sum of the forces in the y direction, right, and this AC FACY is equal to 1.5 kilonewtons. the 3, 4, 5 triangle, right? 3, 4, 5. So my force in AC is equal to 1.5 kilonewtons times 5 meters over 3 meters. Two and a half kilonewtons. It's in tension, right? Sum of the forces in the x direction. I've got negative 4 kilonewtons. Plus FACX plus FAB is equal to 0. The horizontal component in member AC and member AB, which is only horizontal. So FAB is equal to 4 kilonewtons minus FACX, which is equal to what? 1.5 kilonewtons. That's the vertical component times 4 meters over 3 meters. So I get a force in AB equal to 2. So it's also in tension. Right? This is in 2.5 kilonewtons. This is 2. And if I look at joint, right? Joint B, I've got let's go back up. 1 point, I've got 1.5 kilonewtons acting up. This member AB two kilonewtons and FBC. It's FBC better be equal to, actually it's going to be in compression, right? Because I have the vertical, it's going to be equal to 1.5, and the horizontal equal to 2. So FBC is equal to the square 2 kilonewton squared plus 1.5 kilonewton which is 2.5. I'm going to make it negative because it is in compression. I could have also done, what, 1.5 times 5 over 3, or 2 times 5 over 4. Yeah. So that is solving my real system. Now I want you guys, okay, so here's my virtual system. So the goal is to find the vertical displacement at joint C. So what I'm going to do at joint C, I'm going to apply a unit load. Now I want you guys to go ahead and solve for the member forces. Okay? I'm going to tell you what the answer is at the end, but I'm going to give you a few minutes to do it. Okay, so that was 5 minutes. If you haven't solved the system, go ahead and pause and finish. I'm gonna give the answers, and I think it's, you need to go back and check what you're doing. You have a reaction of 0.5 newtons. And not newtons. There's no units. These are unitless. 0.5 force. Negative 0.833. Negative 0.833. Positive 0.667. Alright, it's symmetric. You applied a symmetric load. You got symmetric forces, symmetric reactions. So if you need to solve that on your own again to get those numbers, please do. So, okay, now that I've solved my real system and my virtual system, I'm going to come back here and fill it in. I've got member AB, member AC, and member BC. If I go and look at my virtual system, that's the first thing I want to find out is the internal forces in my virtual system. Member AB is plus 0.667. And this is unitless, remember. AC and BC are both negative 0.833. Looking at my real system, I have AB is plus 2.0 kilonewtons. AC is plus 2.5 and BC is negative 2.5. So length AB is just 8 meters. I didn't really need to write the kilonewtons there. AC, we have a 3, 4, 5 triangle, so 3, 4, 5. AC is 5 meters long, and similarly BC is 5 meters long. All of them have the same area, and I'm going to do some unit conversion here. Right? My area is equal to 400 millimeters squared, and I want to get it in meters, so 1,000 millimeters in 1 meter. 4 times 10 to the minus 4th meters squared. Now my elastic modulus is the same for all members as well, and I want to actually get it in kPa, and you'll see why in a minute. But I want to get it in kPa. And it's equal to 200 gigs, 200 gigapascals, and 1 gigapascal has 1 times 10 to the 6 kilopascals, so 200 times 10 to the 6 kPa. And now I just need to multiply all of those together. So let's see, for each member, I get to calculate the contribution of that member to the vertical displacement at C. So plus 0.667 times plus 2 times 8 divided by 400, or I'm sorry, 4 times 10 to the minus 4th times 200 times 10 to the 6th, I get plus 1.33 times 10 to the 4th. If I do the same thing for AC, negative 0.833 times positive 2.5 times 5 divided by 4 times 10 to the minus 4th times 200 times 10 to the 6th. I get negative 1.3 times 10 to the 4th. And if I do the same thing, I'll get positive 1.3 for member BC. So basically that means AB, let's see, AB is in tension, it's elongating in the real world, right? Let's look at that. AB is positive, it's in tension, it's elongating. AC is in tension, as you expected. BC is in compression. And those two are canceling each other out. The fact that AB is elongating means that C is coming down. If you add those together, you get plus 1.33 times 10 to the 4th. Now the question is, what are those units? Right? So let's see, I've got little n, big N, L over A, E. Little n is unitless. Big N, I have the units kilonewtons. L, I have the units M. On the bottom, I put meters squared and then kPa. Why did I do kPa? Because kilonewton, a kilopascal is a kilonewton per meter squared. A pascal is a newton per meter squared. So, kilopascal is a kilonewton per meter squared. Get to cross some stuff out. The kilonewtons, my meter squared. My deflection is in meters. So ultimately my answer gets to be, my deflection at C is 1.33 times 10 to the 4th meters, or multiply that by 1,000, 0.1133 millimeters. next question is, what about that plus sign? Why is it positive? What does that mean? That means it is in the same direction means my displacement means delta C in same direction as my applied unit load. If I go back down to my virtual system, I applied my unit load in the downward direction. So I'm displacing 0.133 millimeters down. And this is my answer right here. If that had come out negative, that would mean my displacement was in the opposite direction of my unit load that I applied, and which would be up in this case, which doesn't really make sense, but you know, that's what it would mean. Might also mean you did a math problem or math error somewhere. So that is how we apply the concept of virtual work to trusses to determine the displacement of their joints. Okay, thank you.